So let's check out with this how this load is distributed in the water tank, which is underground. Let's draw a plan of the tank. To keep this lecture to the point, we will only discuss here about the tank which has two-way slabs only, all vertical walls, all vertical walls, top slab and bottom slab is only two-way. So we are discussing only two-way slab uh, water tank, not the one way. The one design for the one way water tank is little different, and it is also not in conduct practice. Most of the water tanks are two-way in nature only. So this is the two-way water tank. This is the plan. So let's assume a condition when water is completely filled. You are your water is acting. Just mark this. This is the water pressure acting per minute on the wall, right? This is the case. Another case is you have a water tank and soil is acting from outside, right? This is soil which is acting from outside. Now let's draw some reflected shape. So because of this, these edges are little fixed with these edges. This edge is fixed here and this edge is fixed here. So the reflected shape will be something like this. Let's choose a different color. So the reflected shape is like this. Here it is also like this. Here we maintain 90 right? This you must be already knowing. Here what is the reflected shape? Here it is like this. Right? So what is the value of this pressure force that is acting? Density, unit weight. So you must be knowing that if you have this vertical wall, let me just tell you briefly what we are going to do here. See, we have this vertical wall, and this is fixed at ground, and here we have this water pressure, right? So how this water pressure of density gamma W, this load will from this wall, it is triangular in nature, which is gamma W H. If the soil is also there, see water is there and soil is also there. Just submerged soil. See this we are marking for soil, submerged soil. So this density of the water is gamma W. Density of the soil is say gamma soil is saturated. So this saturated soil will act as effective. This density of the soil will be effective now. Okay, in terms of pressure, gamma dash into H, right? Also, there will be a coefficient of Ka, which is active earth pressure. So the total coefficient when there is a submerged soil acting on the on this wall, then the total coefficient here is Ka gamma dash of the soil plus gamma W, right? And what if only water pressure is acting? Then the coefficient is only gamma W, right? So what we see here is here the coefficient of pressure is Ka gamma soil effective plus gamma W. This we will multiply with the moment coefficients. Here what we will multiply, we will only multiply gamma W. So what is critical? It is simple. This is critical, right? This is critical. So we will start designing with this load case for underground water tank. If this is not underground, definitely this is the only governing case. So that is not a question at all. For our case, this is the critical case. So we will design when water saturated water soil pressure is acting from outside. So this is our method of design for walls. Now come to the uh, base layer. So let's draw an elevation of the tank. Okay, we have this. Let's do not draw this overhang. We will just simply draw a tank. We have this wall. This is the base layer. So this is the total. This is the base layer. Okay? So what is happening here? We have this base layer. We have this wall. This is a sectional elevation, and we have this water pressure acting from outside. Water pressure as well as soil pressure, right? This is water as well as soil pressure acting from outside on the wall, right? Suppose there is a case when it is completely water is completely submerged and this tank is empty. There is no water inside. There is no any other liquid inside. Aqueous liquid or non-aqueous liquid is there inside this tank. Then there is also an uplift pressure of water acting at the bottom. So we should make this uh, tank such that even if it is empty, there is no flotation. So we have to check certain factors of safety. We have to make sure the factor of safety FOS are greater than 1.2. The factor of safety is major factors of safety are number one, uplift. There should be no uplift when tank is empty. There is no sliding. There is no overturning. Right? There are generally two ways to avoid this uplift because this is the most important part of the design. This uplift is the most critical also. This is very critical. Why? Because there are only two ways to arrest this uplift. The first one is you increase the base weight of the total self weight of this assembly walls, all the peripheral walls, base slab and top slab. You increase the weight. The weight increasing means you are increasing the area of the base slab. The If you increase this, you will have to add this additional concrete, right? You will have to bear this cost. You have to increase the wall thickness, right? To increase the weight. You'll have to do more digging and then more excavation is required. So it is not the right practice to do that. What is the right practice? See, the right way of doing and avoiding uplift is providing the overhangs. What happens when you provide these overhangs? Let me just tell you. See, we have this. What a time. If we provide this overhang of some length, okay, and this is the ground surface soil. So this soil is acting loaded on this overhang. So this soil is providing the counterbalance. So when this is trying to uplift because of water pressure, this soil which is on the overhangs will resist it, right? This soil on the overhangs will resist it. And because of this, the volume of the concrete that is required in design is sufficient enough to arrest the crack width and to counter the moments. So only that much required thickness of the raft will provide, which is sufficient for the crack width limitations and for the reinforcement requirement as per the moments induced in the uh, raft. In the raft. Assume this case. Take this section, okay? In this section, this part of the slab is acting as a cantilever. This load is acting and this will try to deflect it like this, right? So where do we need the reinforcement? Also, we provide the reinforcement in this case also because of sometimes when whatever sometimes what happens is there is a reversal of stresses when tank is unloaded. So to account for that, we provide reinforcement, equal reinforcement in both the phases. Similarly, the next critical phase portion is this one, center of the raft, where we will see there are all the moments and loads we will calculate and find out the critical moment. And the critical moment that will occur is uh, occurs at the center of the raft. And this will work out for this reinforcement. We will provide for this moment. We will provide reinforcement at here and here. Okay. So this is how we will design the raft. Now we will come to the top slab. Top slab, as we already discussed, is a two-way slab. So this is L, this is B, and this is the top slab. Top slab is L by B is less than 2. This we will refer IS 456 standard procedure. And table is given in IS 456. You see here. Hmm, see this slab is running in two directions, left should be. So this table we will use and do the design of two-way slab. Right? More others discontinued. This is the case that is the governing case for us. These are the values. Okay. So this you will utilize in design of the top slab. So this is about the basics of tank design, right? Let's